Good morning. Um, Welcome back to a pretty chaotic week. Um, Good news is that I have my life at least a little bit together, and I have a plan for actually what's going to be on the quiz and what we're going to talk about today. So this week was meant to be 2 lectures on 2-3 trees, then heaps, then graphs. I moved heaps forward because I wanted there to be or you guys to get all the assignment material in as quickly as possible. And then I wasn't sure what I was going to do next, and I have no idea what's going to be on the quiz. I've decided I'm going to keep talking about 2-3 trees today in order to make it so the quiz just gets all of the 2-3 tree questions out of the way, instead of having very basic questions on both 2-3 trees and graphs. So I'm not sure if tomorrow's lecture even has any testable material. So yeah, we're going to talk about 2-3 tree deletion today. The content on graphs, that'll be on the assignment. I'll definitely cover it on Thursday, maybe today if I have time at the end of class. But I really don't think it's the end of the world if you aren't introduced to it very soon, because there's nothing specific to this class regarding graphs that you need to know for the assignment. You just need to know, it's a bunch of vertices connected by edges. Hopefully you'll already learn that in a discrete math course, and with that combined with your knowledge on asymptotic notation, you'll be able to get started on that assignment question without me telling you a word about graphs in this class. Of course, the final will have stuff to do with graphs that are specific to their implementation and data structure stuff, but that's not something you need to worry about right now. Yeah?
Were there recording questions in the quiz?
I don't know. Wait. I don't know. I should probably give you guys a break. I know I want a break. I'll decide later, maybe even later this lecture. We got to talk about 2-3 trees, though. As a little warm-up, let's find a number such that inserting it into the tree causes the height of the tree to increase. We saw earlier that the height of a 2-3 tree increases relatively rarely, and it does so in a way that makes it so the tree structure is always balanced. All paths from the root to any leaf are of the same length. All these lines I'm drawing are made up of 2 edges. So how will we cause the 2-3 tree's height to increase? Well, let's look at the tree a bit. We know that when inserting an item into a 2-3 tree, it sort of moves down the tree and gets inserted at a leaf node. So maybe if we try inserting 24, this is a bad guess, but bear with me. We'll start here. It's greater than both 11 and 22, so we go to the right. Less than 26, so we go to the left. And then this leaf node becomes, now holds both 24 and 25. Nothing really happened. But if we insert a value such that it goes into a node that already has 2 values, it'll make a value sort of bubble up. So maybe 31. That will be inserted right here by you're hopefully used to by now. And then out of these 3 values, 30 will get moved upwards, and then 27 and 31 will go into their own separate nodes. There are now 3 children of the node that contains 26 and 30. But that doesn't really do anything. To cause the height of the 2-3 tree to increase, we need to find a possible insertion such that a value goes up from the leaf node, and then it also goes up from the middle node, causing the value to go up from the root node and increase the height of the tree. So with that in mind, the choice is somewhat clear. We should insert a value that would go right here, because then this node will contain 3 values. One of them would have to move up. Then this node would contain 3 values. One of them would have to move up. And then this node would contain 3 values. One of them would have to move up into a new root node, making it so the whole tree has its height increased. The official answer to this is 6. Any number that would be inserted into that leaf, though, would work. We see here from it having 2 and 8 that anything between 2 and 8 would work. So the 6 is inserted after the 5, leading to that leaf node having 3 values. We call that an overfull leaf. 5 will get pushed up, and 4 and 6 will become separate nodes. Now we have a node with 3 values and 4 children. No good. And we repeat this process as many times as it takes until all nodes are in a valid state. So with the red node seen here, we're going to push 5 up and then split the remaining nodes. They'll end up looking like this. And voila. Now the root node has 3 values and 4 children, and we do the exact same thing. 11 is going to become the new root. It will have children 5 and 22. 5 will have these 2, and 22 will have those 2. Ta-da! So hopefully this was a decent illustration of how the rules of 2-3 tree make it continue to be balanced. Like, it definitely wasn't obvious from the start that making it so nodes can have 1 or 2 values and 2 or 3 children really does anything. But as you could see here, the height of the tree will only increase in certain cases, and it'll only increase from the top, keeping the height consistent for every path from the root to a leaf. But on to the good stuff. The delete operation is a good bit more complicated than a binary tree's delete operation, but you already have the foundation to begin to understand it. It starts off similar enough to the binary search tree deletion algorithm. You have to search for the value to be deleted, and then if the value to be deleted is in an interior node, like say the value we want to delete is 18, then we would swap it with its immediate successor, which must be in a leaf node. We won't be covering the details of that successor operation because it works in the exact same way as that of a binary search tree. Actually, it's a tiny bit simpler because the way 2-3 trees are set up means that if a node is an interior node, so it's not a leaf, it's guaranteed to have a right child, and thus you only have to worry about one case of that successor algorithm. I remember we had to balance if it doesn't have a right child, you go up the tree, and if it does, you go down the tree, blah, blah, blah. No need to worry about that. Another way that the delete operation for 2-3 trees is similar to binary search trees is that there are a few cases that we need to worry about, some much easier than others. I would even say that the easy case for 2-3 trees is even easier than that for binary trees. The hard case is much harder though. The easiest case comes in when you have to delete a value that is in a node that has two values. So in this case, we're going to delete 19. 19 shares a node with 21. So we're just going to delete the 19, keep the 21. It's easy. Because of that thing I just talked about with swapping with successors, that preliminary step makes it so the node we're deleting is always in a leaf node. And thus, for this case, we don't need to worry about the restriction that the nodes can have 2 children if they have 1 value or 3 children if they have 2 values. Just delete it. Go from 2 values to 1. Slightly trickier is when you're deleting a value that occupies a node by itself. This is kind of analogous to the easiest case for binary search trees. In that, we could just delete that node and move on with our lives. But that would break the 2-3 tree structure. 18 would have 1 value and 1 child, which would break the rules and lead to all sorts of evil consequences, like having O of n searches. So we need to sort of restructure the tree to keep up the structure that we care so much about. In this case, a sibling of the node contains 2 values, and that's more values than it needs. It could have 1 value and the tree structure could remain the same. So we're going to kind of sort of borrow a value from that neighbor, more like take a value. Basic idea is that, next slide will be better for demonstrating this. After you delete 21, the node that used to contain it would contain 0 values, which is bad, and its sibling would have 2. So we could just make it so the sibling has 1 and the node we were working on also has 1. First attempt at doing this is to just move a value directly from the sibling, but you may have noticed that 15 is less than 18, so this would break the ordering of values that we want for 2-3 trees. Instead, we're going to sort of redistribute the values. 18 gets pulled down from the parent, and then 15 gets pushed up from the child. And because of the ordering of values within 2-3 trees, any reordering of values within this subtree won't break any properties of the tree overall. All these values are still in between 11 and 22. So this is the result of the redistribution. We took 18 down and 15 up, and got this as our result. Here's another example of this trickier case, and it's about to get even trickier because with this example, it was obvious which values to redistribute. There's only one choice. The fact that the parent of 1 has 2 makes it slightly more ambiguous. So we're going to delete the 1 and then redistribute the parent and sibling values. I said this was more complicated, but it's not that much more complicated. Just take the minimum value in the parent, move it down, and also the minimum value in the child and move it up. This preserves all the properties of number ordering that we want. And actually, I'm going to go back up through some of these slides and keep my annotations with the arrows because I think they might be helpful. Bada bing, bada boom. And now we're at the trickiest case. We want to delete 5 from this tree, but that node only has 1 value, and so do all of its siblings. So obviously the first step is to delete that value, but what do we do now? We probably want to move a value downwards, but then the parent node will have 1 value, and thus having a middle child would be meaningless. So maybe you would want to pull down a value from the parent, but then you'd have 11 in the parent and 10 in the right child, and that would break ordering. We'll have to follow a tricky algorithm. It probably took a while for the inventors to think of this. I can totally imagine them trying to figure out a way to move values around with the same number of nodes and getting really stumped, and then having an aha moment where they go why do we have to keep the node? We're going to, this might be a bit misleading, but we're kind of deleting the node itself. Before, we would just delete the value and keep the node. But now the node itself is gone. But that description wasn't very good. I think there's going to be an example later in the lecture that shows why we're not really deleting those nodes, more like merging. But I'll explain why that explanation can sometimes fail if there isn't an example that explains it itself. For now, the node with 5 is gone. We merged the empty node with an adjacent sibling. And then things are getting a bit better. We still have a node with 2 values and only 2 children, which is bad. But now we can pretty easily fix this. We're just gonna move a value down. Also, I'm going to draw an arrow here. It'll make sense later. So we pull down a value from the parent node. Whether you want to call it merging or deleting, the tree now has one less node than it started with. It's kind of funny how that would happen all the time in binary search trees, but with 2-3 trees, you might get so used to just deleting values from leaf nodes that already have 2 children, that it can become a novel idea again to actually reduce the number of nodes in the tree. So let's go through another example. I think this is the one that'll show why my explanation of deleting a node wasn't very good and why it's better to think of it as merging. So we're going to delete the value. Now has an empty node, which will be merged into an adjacent sibling. Again, right now this is indistinguishable from just destroying that node, but trust me, we're actually merging it. And then we're going to pull down a value from the parent, but our tree is still a little messed up. We went from a node in an invalid state because it had one value and one child to a node in an even worse state where it has 0 values and 1 child. But this situation is basically the same thing as what we got ourselves into earlier. We have an empty node. So this is the thing I was building up to. Previously, we would move the empty node, merge the empty node with its sibling, and it would look like it's just being deleted. Now, we're going to merge the empty node with a sibling, and then thinking of this as a deletion wouldn't really make sense because its child values should still be in the tree. And they stay. Oh wait, I should probably apply this arrow to another slide. So we merged it. This time there's actually a distinction between deleting and merging, because this time doing that sort of merge preserved the formerly empty node's child node. So this is looking slightly better. At least we don't have any empty nodes anymore, but we still have a node that is in an invalid state. Evil little 8 here has 1 value and 3 children. That middle child is meaningless. So, and also, the root has 2 values and 2 children. This isn't as apparent, as severe a problem as a node having 1 value and 3 children. In 8's case, like that middle child is completely meaningless, but here, I don't know, the binary search tree property still works. But we need to keep the tree completely balanced. So our next step is going to be to pull a value down from the parent. This is actually the exact same procedure that we did earlier. We deleted a node, or deleted a value, merged the empty node with an adjacent sibling, and pulled down a value from the parent. And then we were left with another node in an invalid state. Tongue twister. So we do the exact same thing. Merge the node with an adjacent sibling and pull down a value from the parent. Ta-da! So we just keep doing this until no empty nodes remain. The lecture doesn't talk about its time complexity, but you could imagine that a delete operation, in the best case, just goes ahead and deletes. But the worst case involves moving up the entire height of the tree, doing a bunch of operations along the way. And thus the worst case of the deletion algorithm would be proportional to the height of the tree, big O of log n. Of course, the deletion algorithm probably involves searching for the thing you're going to delete, so it's going to be O of log n anyway. I realized that as I started that tangent about deletion. Oh well. So, we're at the end of this lecture. That was surprisingly quick. And now I'm not sure whether it would be better to do more 2-3 tree examples or do graphs. Does anyone have any strong opinions on this?
Can you do one more? Like, at least 2 examples of 2, 3 trees and then one.
Sure. Did you want examples of insertion or deletion? Please say insertion. I don't have any more examples, but I could maybe just improvise. Okay, so deleting 25 would give us give us a slightly tricky case. Deleting 27 or 30 would give us the easy case. I want to see if there's one that would give us the hard case. Yeah, I don't think I have much to work with this graph, actually. I'll go through examples with the first 2 cases, but I don't think any values on this tree would give us, like, the hard cases.
So like, if you try to delete 26, so then 25 would just jump up?
Actually, that would have to do with a detail from the very start that we kind of skipped over. If the value to be deleted isn't in a leaf, we swap it with its immediate successor, which must be in a leaf node, and then do the delete operation as planned. So, starting with this graph and deleting 26, we would find its successor. Luckily, it's really easy here. The minimum value of the right subtree is 27. So we would swap 26 and 27. And then, from there, deleting 26 would be the easy case. It shares a value, or shares a node with another value, so we could just go ahead and delete it. I'm going to see if the tree from the start of the lecture has anything worth using. No. I've got nothing because I don't want to make a new tree, but I don't think there are any values in this tree whose deletion would cause the hard case. I'll give you something as a consolation, though. There's a very helpful tool online. Computer Science at USF. This website in general is great, but it basically lets you run through different data structure operations and with animations too. Note that this isn't technically for 2-3 trees, even this specific page. Instead, it's for B trees, which are like outside the scope of this course. You might learn about them in more detail in a 4th-year databases course. But 2-3 trees are a specific type of B tree where the max degree is equal to 3. So this website will let you work with 2-3 trees anyway, even if it doesn't say the name. No. Dang it, I don't think this will give me an actual keyboard. Okay, phew. So as you can see, this doesn't work perfectly on touchscreens, but if you go onto this on an actual keyboard and mouse computer, you'll have a great time. I'm just going to add some values to it to demonstrate. So when we insert 4, it's going to make the 3 bubble up, and then 2 and 4 will have their own nodes. Ta-da! And notice that slick animation. Then I'm just going to insert some other values. Yeah, stuff like this. And then I think at this point with this tree, if I were to delete any one of these leaf node values, it would cause the hard case. Like say if I deleted 2, then that node would merge with 4, 3 would be pulled down into it, and then 5 would be the new root by itself. But let's confirm this. I said we'd delete 2, right? Yeah. So, hope you accept this in lieu of me doing any actual examples. This site lets you visualize data structures and their operations, and I highly recommend practicing by going onto this site, making a data structure, trying to predict the results of its operations, and then using this to verify, like I just did. And like this place has visualizations for a bunch of other things, including other data structures from this course. Oh look, stacks and queues with multiple implementations. Heaps, graphs, and that looks like it. So, hopefully that was fun enough. Let's talk about graphs. You should look at the list of lectures on UM Learn to confirm this, but I'm pretty sure this is what was scheduled for Thursday's class, and thus nothing about graphs in general will be on the quiz. We're working ahead, and like I mentioned last week, hopefully we'll get to the point where we're exactly a day ahead, and then the cutoff for the next quiz will be Tuesday instead of Wednesday. Hopefully. Graphs. The definition we're going to use is that it consists of a set V of nodes, also known as vertices. I'm going to mix them up and use those terms interchangeably all the time. But in general, we say nodes when we're talking about like programming and data structures, and vertices when we're talking about graphs in a more abstract mathematical sense. I'm going to mix them up. So anyway, a set V of nodes or vertices and a set E of edges, where each edge, E as an element of big E, represents a relationship between two of the nodes in V. So as an example, one example is right here. The empty graph is a graph. In terms of its mathematical definition, this is just two sets, two empty sets. By some definition, it might be an ordered pair of sets, but this doesn't specify. The next example is a graph with one node and no edges, like that. And a more interesting graph with 4 nodes and 6 edges. So each of these labeled circles is a node. Nodes may or may not have labels. Depending on their context, they might just be empty circles. They might have letters, they might have numbers, they might have other data. In this case, we're using letters because it's easy to understand. And then the 6 edges are the 6 lines connecting them. Like that. Each edge represents a relationship between two of the nodes. In this case, we're literally just looking at circles and lines. So the relationship here is these two circles have a line between them. But graphs are like hella applicable to a whole bunch of contexts. And this thing sort of just works to represent any set of objects that can be related in pairs. The two applications of this that I like to use most when talking about graphs are transportation and social networks. So in the transportation metaphor, each graph would be a building, and each edge would be a road between them. Actually might make more sense to have the nodes be cities and the edges being highways between them. Whatever. They're places that are connected. And then in social networks, the nodes are people, and then the edges are some sort of relationship, like they're friends, or they went to the same school, or something like that. I'm going to be referring to those two metaphors a bunch of different times throughout the lectures on graphs. This slide just shows some edge cases of graphs, things that are technically possible but don't actually show up very often in the study of graphs. You could have a loop that connects a vertex to itself, and also multiple edges of having two nodes being connected in multiple ways. these both kind of don't make any sense within either of the metaphors that I gave. Like, will a city have a road to itself? Can a person be friends with themselves? Can a road or a city have two roads between them? Can two people be friends twice? Of course, some contexts still have this make sense. Can I think of one on the spot? Nope. Except maybe multiple edges. We're going to find a version of graphs later that has, or it's called a weighted graph, and it makes it so every edge is associated with some number. So like maybe 10 and 20. And then I guess this would make multiple edges make sense in a transportation context. Maybe there are multiple roads connecting two cities. Maybe the longer one goes through some destination in the middle. But really, you don't need to worry about this part that much. Each node has a degree defined as the number of edges that are incident with this node. Totally implicit is the definition of incident. How can I succinctly say that? Well, informally, an edge is incident to a node if it connects that node to something else. So this edge, the one that I just circled, is incident to A and B. If you learn about graphs in the context of like a more formal math course first, they'll probably give a more specific definition. And it would depend on the definition of an edge. This is kind of rambling. I kind of want to just talk about definitions, so bear with me. Oftentimes, edges are defined as sets that contain two vertices. So this edge would be the set AB. And this would give us a really easy way to define incident, as in an edge is incident with a node if that edge contains that node. The edge AB is incident to A because it contains A. But apparently you weren't supposed to know this, so incident isn't going to have a good definition. You just have to vibe with it. So yeah, the degree of the node is the number of edges that are incident with that node. In the first example, the degree of every node is 3. Social network metaphor. In this example, there are 4 people and they're all friends with each other. They each have 3 friends. And then in the second example, poor B has no friends. It has nodes of multiple different degrees. A has degree 1 because there's 1 edge to it. D has degree 1 for the same reason. B has degree 0 because no edges are incident to it. And C has degree 2 because of its 2 edges. C is very popular. In the transportation metaphor, you could think of B as maybe being a city that is on an island. Cities A, C, and D are on the mainland, and they have roads connecting to them, but to get to B, you'd have to go by boat. B for boat. There are many different ways graphs can be applicable to different situations. As you're studying, maybe even try to think of your own. Oh yeah, when an edge forms a loop, we say that that edge is incident with the node twice. So in that slightly more formal definition, this edge would be the set A. I guess it would be a multiset, and we would count the fact that it contains A twice to say that the degree of A is 2. And a neat fact is that if you add up all of the degrees of all of the nodes, you'll get the number of edges, or 2 times the number of edges in the graph. That's because every edge is incident to exactly 2 nodes. So if we add up all the degrees, you count each edge exactly twice. Yeah?
If we do know some formal graph theory, are we allowed to use that?
Ooh. Probably look at that on a case-by-case basis. I'm trying to think of an example where it would be bad, and I'm kind of blanking.
Okay. On the previous graph, we're talking about vertex B and say it's isolated.
Oh, okay. Oh, okay. I would caution away from that, not for any not for any good reason, but just in case the marker doesn't understand you, you should only assume that the marker has taken, they've been educated up to this course, but you can't assume any farther. So you should stick to the relatively basic graph theory that we're learning in this course, just in case, because if you use advanced stuff, you risk confusing the marker and losing marks over it. Which is a bit of a shame, because I have no moral objection to flexing higher level knowledge of this stuff when working on relatively basic problems. But we're in a school system, and I don't want you to lose marks that you don't have to. More definitions. A path through a graph is a sequence of distinct edges connecting one node to the next such that each node on the path is visited exactly once. We'll go back to that big slide later. Don't worry, I'll read the whole thing. But in this example, A, B, C, E, F is a path from A to F. Different paths exist. A, B, E, F is also a path. It is also a sequence of distinct edges connecting one node from the next such that each node on the path is visited exactly once. Whew. This is sort of the strictest notion we'll see of sequence of edges connecting one node to the next. All these other ones are sort of relaxations of that definition. A trail is a generalization of a path where the edges are still distinct, but some nodes may be visited more than once. So let's see, can I make a trail here? I don't think any interesting trails exist on this graph. Of course, something like A to B is technically a trail, but it's not interesting. There's nothing separating it from a path. So I'm just going to draw one more edge. Pretend that B and D were always connected. They're pretending to be friends. And now I can define a nice trail of A, B, E, C, B, D. Yeah, I think that's the best picture I'm going to draw. Notice how all of the edges were distinct. We never traversed the same edge twice. But we visited the vertex B multiple times. All these definitions don't make much sense for social networks, but you could totally imagine them representing some sort of trip, like in the transportation metaphor. And again, try to think of other examples. I'll give you one example, actually. Anyone studying computer networks will use a lot of graph theory in which the vertices represent computers and edges represent network links between them. So if A wanted to send a message to F, it's a well-studied problem. It's a relevant problem to know the network topology. That's a fancy term for what the network would look like represented as a graph. And then figure out the shortest path between those two computers on the network to send that message. We're actually going to cover an algorithm for finding the shortest path between two nodes later in the course. Anyway, a walk is a further generalization of a trail in which some edges may be used more than once. So you could see that is like a further relaxation of the old definitions. Path required no repeated nodes, which actually implies no repeated edges. A trail allows for repeated nodes, but still doesn't allow repeated edges. And a walk lets you repeat either one. So I'm just gonna go for a walk. It's casual. A, B, E, C, B, E, D, E, D, E, B, C. Like, no real structure is imposed on this. And finally, a cycle is a trail that starts and ends on the same node, but contains no other duplicates. So it's technically a trail, but I prefer to think of cycles as a step away from paths. You might think about it in a different way. It's fine. But the slide says a cycle is a trail where there's only one node that can be repeated. I like to think of it as a path where there are no duplicates except that one node that can be repeated. So this slide gives a cycle. B, C, E, B is a cycle in. Note how we didn't repeat any vertices except for the start and the end, which were both B. And also, since we didn't repeat any vertices, that automatically gives us the fact that we didn't repeat any edges. Because to repeat an edge, you have to repeat the two vertices that it's incident to. And as a demonstration of how you can't repeat stuff in a cycle other than the beginning of an end, B, C, B is not a cycle because it repeats an edge. It doesn't technically repeat vertices other than the start and the end, but it manages to repeat an edge anyway. Graph is connected such that there exists a path between any pair of vertices. So, like, you could choose any two vertices in this graph, and you'll be able to find a path from one to the other. A to D, you could go like this. C to F, you could go like that. B to E, easy. And in contrast, a disconnected graph has at least one pair of vertices that cannot be reached from each other. If you start at B and you want to reach E, using only the connections in this graph, you're hopeless. As the picture should illustrate, it's impossible. Yeah, by the way, this lecture is pretty much entirely definitions. Similarly to the asymptotic notation definitions, you won't necessarily need to memorize anything, but you should still understand these definitions well enough to recognize them. You may be asked to draw a complete graph, and you won't be required to repeat. A graph G equals VE is complete or fully connected if for all x, y, and v such that x is not equal to y, there is an edge in E between x and y. You won't have to say that, but you might have to draw something like this. Memorize nothing, understand everything. This graph is complete because there's an edge from every edge to every other, edge from every vertex to every other vertex. And the graph on the bottom is not. There are no edges between C and B and A and D. Note that there is still a path between them. Like you could get from A to D through C. But there isn't an edge immediately connecting them. So the graph on the bottom is still connected, but it's not complete. Oh, look, trees. Wait, does it have any example that are trees? Yeah. So it's a connected acyclic graph. Guess it doesn't have to be directed anymore. Mathematicians often disagree on the exact definitions of things. And yeah, this definition doesn't mention directedness. If I teach this course again, I'm probably just going to edit those slides on trees to make it so the original definition doesn't require them to be directed, because it never comes up. Whatever. These should remind you of that one quiz question where you had to tell whether a graph is a tree or not. And there was one part of that question where a graph didn't look like a tree. Given this, it's kind of hard to figure out what is the parent or child of what. But it, totally is a tree. It is a connected, acyclic graph. And I guess the notion of trees being directed can be useful in that it gives you an objective idea of what the parents and the children are. So in our discussion of binary trees and how to search them, it was important that specific nodes were parents of others. But this graph and this definition doesn't specify that. So where do I draw this? This graph or this tree can be drawn like I did, but it could equally validly be drawn like this. So is C the parent or the child of B? This example doesn't specify, and this definition doesn't specify. So yeah, I guess it doesn't really matter, or no, it does matter. The definitions of certain terms can differ based on whether you're thinking of them in a more mathematical context or computer scientific context. And we could say that trees in computer science are directed because it's very important to know which nodes are the parents or children of one another. But a tree in math isn't directed because we just don't care. Extra definition, I might have mentioned this before, but it doesn't appear on the slides. A graph like this, that is basically a tree, but it's not connected. You could look at this as a collection of trees. Oh wait, don't spoil the definition I was going to say, but did you have a different question?
Yes. But go ahead and finish.
Okay, sure. This looks like a collection of trees. Each of its connected components is a tree. So what do you call a collection of trees? A forest. Anyway, what was your question?
Going back up, we were talking about how many different ways to arrange the trees. Right?
Mm-hmm.
How many, given n vertices, how many different ways can we do that?
Holy moly. I have no idea. But my first thought is that it might not depend on the number of vertices, but the number of edges, because for each edge in the graph, you can make a choice between possibilities of which one is the parent and which one is the child. So my basic guess, I've never thought of this before, is that it's probably 2 to the power of the number of edges, because you're making a choice between two things for each edge. And you're making that choice for each edge. Yeah.
How would you prefer if you connected any which way you want to do it just trees?
Oh, so rather than... Wait. So I was thinking it in terms of, given a specific graph, how many different directed trees can you turn it into? But you're thinking of just given a bunch of vertices, how many trees can you create? Oh, okay. I'll try that one. Well, for starters, the number of distinct graphs you can make. Oh, and by the way, these vertices are considered unique. This will definitely overcount, but the number of distinct graphs I can make would involve going through all pairs of vertices and deciding whether to put an edge between them. So that would be 2 to the power of the number of vertices. But that's definitely super overcounting, because many of them will involve cycles, and they may or may not be connected. And from there, I think that exceeds the amount of brain power that I have while presenting. Anyone who's done a class presentation knows this. You lose half your brain cells when you're in front of a classroom. That doesn't change when you become an instructor. So I'm gonna give up here. I'd be happy to talk about this in office hours though. Oh yeah, subgraphs. So if you have a graph VE, remember V is the set of vertices and E is the set of edges. Another graph, G prime, is a subgraph of G if its vertex set is a subgraph or is a subset of the original vertex set, and its edge set is a subset of the original edge set. So if we start with the graph G shown on top on this slide, the graph below is a subgraph of G. I'm just going to write down the vertex and edge set for both graphs. And I might regret this, but anyway, V's vertex set is just the letters that make up its vertices. Then its edge set is a bunch of two-element sets that represent the edges that exist there. And note that all of these sets of two vertices correspond to an edge in the graph. Like, there is no subset AD because there isn't an edge from A to D. But if there was, it would be in the edge set. So hopefully that's everything. 6 edges. 1, 2, 3, 4, 5, 6. Probably. The reason I went through all that is just to illustrate that in the subgraph of G, the new vertex set is a subset of the old vertex set. Hopefully you took Math 1240 and you know what a subset is. And the edge set is the same. Every element in these prime sets is also present in the set that they are subsets of. Swoosh. A spanning tree is a graph such that, well, for starters, it's a tree. And if its edge set is a subset of another graph's edge set, and its vertex set is the exact same as another graph's vertex set. I went through that kind of backwards. We have a graph G and a graph T. T is a spanning tree if T uses the exact same vertex set as G, and if T's edge set is a subset of G's edge set, and also that T is a tree. In contexts like transportation and computer networks, it's a very common task to find a minimum spanning tree. I'm going to spoil weighted graphs again. So like, say, connecting from B to E takes 100 milliseconds. This is a computer networks metaphor. We're talking about like computers talking to each other. But then B to C have a 10 millisecond ping. I don't actually play computer games. I don't know if these are good numbers. I just play single-player RPGs. So yeah, if you have a situation like this, a spanning tree would give you the infrastructure to always choose a shorter path from one node to another. A minimum spanning tree specifically. But again, we haven't actually looked at weighted graphs yet. I'll define them in more detail when we get to them. Oh, look, graphs are often used to model transportation. That's crazy. And sometimes destinations have different distances between them. Well, look, it's weighted graphs. So this definition, I think is a bit too rigorous for its own good. Like this is great if you're getting your bachelor's in math. It's a graph together with a weight function, mapping the edge set of a graph to the real numbers. But that kind of obscures what it's actually doing, which is assigning a weight to each edge in G. Each edge in the graph has a number associated with it. And that's all you really need to know for this course. Don't worry about mapping the elements of the edge set from, or to the real numbers. And it probably needs to be a one-to-one function? No, one-to-one. Yeah, one-to-one function. I don't know. So that gives us a whole bunch of other possibilities for graphs. We can calculate the entire weight of a graph, which is the sum of the weights of all the edges. And more importantly, we can weigh different paths. I already showed an example of this actually, where one path from B to E had value 100 and the other path had value 20. So you would use this object to model situations where one path from one destination to another might be easier than the other. And yeah, as I said before, two problems that come up all the time for weighted graphs are finding shortest paths and minimum spanning trees. We're going to cover an algorithm for finding shortest paths later in the course. And then I think this is the last definition. Whew. With the definition we know so far, an edge from A to B is also an edge from B to A. If we use sets of size 2 to model edges, we kind of get that for free because order doesn't matter in sets. But sometimes it's meaningful to assign each edge a specific direction. So this isn't in the slide and not even required for the course, but you would use ordered pairs to represent these, where order actually matters. In this case, the graph would have the ordered pair AB and not the ordered pair BA in its edge set. So that's all the definitions. You're going to have lots of fun with these next quiz. Starting next lecture, we're going to talk about how we might implement these in code. So yeah, see you tomorrow.